start with the schema theorem of binary coded GA, and this particular schema theorem is going to indirectly prove the convergence of the binary coded GA. Now, let us see the principle of this particular the schema theorem. Now, the concept actually it was given by Professor John Holland, who actually introduced the concept of the binary coded GA. Now, here as I told, the purpose is to investigate the mathematical foundation of this particular the binary coded GA. Now, to discuss this particular theory, so let us start with a population of binary strings created at random. Now, supposing that to start with the binary coded GA, so we have created this particular the binary strings at random using the random number generator. Now, actually what I do is we try to find out the similarity among these particular the binary strings. Now, to define or to explain this particular schema theorem, we take the help of some schema or the template, and schemata is actually the plural of this schema. So, schemata means templates. So, here for simplicity I am just going to consider only two templates or only two schemata. H1 is star 1 0 star star star. Now, star means it could be either 1 or 0, and there are some fixed numbers like 1 and 0. So, star as I told, it can take either 1 or 0. So, this is one schema or one template. Similarly, there is another schema I am going to consider, that is H2, and that is nothing but star 1 0 0 0 0. Now, here there is only one star. Now, the star could be either 0 or 1, and we have got the remaining 5 fixed bits consisting of ones and zeros. Now, if I just try to find out that how many strings which are present in this particular population are going to follow a particular template, that is H1, I can find out. For example, H1 says star 1 0 star star star. Now, if I see the population, the first string is going to follow 1 0 1 0 1 0 1 0. So, all the strings which I am showing here, of course, there are some hidden binary strings here, but all the 4 strings which I am showing here are going to follow. So, this particular the first template or the first schema. Similarly, that H2 is nothing but star 1 1 0 0 0 0 0. So, if I see this particular population, so it is star 1 0 0 0 0. So, if I see this particular thing, so 1 1 0 0 0 0, the second is going to follow that, third is not going to follow, but the last one is going to follow this particular H2. Just to repeat, so all the strings shown here are going to follow that template H1, but only string second and the last one are going to follow that second schema, that is your H2. Now, we define two terms. One is called the order of a schema, that is denoted by OH, and that is nothing but number of fixed position or bits present in a schema. Now, if you see this particular H1, we have got only 2 fixed bits. So, order of this particular H1, that is OH1 is equals to 2. Next is your order of H2. H2 is 1, 2, 3, 4, 5. So, there are 5 fixed bits. So, order of this particular the H2 is nothing but 5, and we try to define another term, that is called the defining length of a schema, that is your delta H, and delta H is defined as the distance between the first and the last fixed bit position in a string. Now, if you just see H1. So, H1, so this is the last fixed bit position and this is the first fixed bit position. So, the defining length is nothing but the 3 minus 2. So, 3 minus 2 will be the defining length for 1, that is nothing but 3 minus 2 is equals to 1. Similarly, if I want to find out the defining length for H2, so the last fixed position is first, second, third, fourth, fifth, sixth position is the last one, last fixed bit, and the first fixed bit is the second position. That means 6 minus 2, that is 4, will be the defining length for the second template. So, delta H1 is equals to 3 minus 2 equals to 1 and delta H2 is 6 minus 2, that is equals to 4. So, I have defined this particular two terms, order of schema, that is OH, and defining length of a schema, that is nothing but delta H. And I will carry out this analysis with the help of these two terms, that is order of schema H and defining length of schema H. Now, I am just going to concentrate on the GA operators, and let me start with the proportionate selection, that is nothing but the roulette wheel selection, where the probability of selection in the mating pool of a particular GA string is proportional to the fitness. The higher the fitness, the more will be the probability of being selected. Now, supposing that MHT is going to represent number of strings belonging to schema H at Tth generation. That means, how many strings are going to follow schema H at Tth iteration, that is nothing but MH comma T. Now, our aim is to find out what is MHT plus 1. That means, how many strings are going to follow the same schema H at T plus 1th iteration. That means, let me take a very simple example. Supposing that the population size of the GA is 100 and a particular schema H is followed by say only 5 GA string out of 100 in first iteration. Now, there is a possibility in the second iteration this number 5 may increase to 8 or it may also decrease to 2. Then how to increase or how to decrease in number? So, that principle I am going to discuss. So, n is the population size, and now I am just going to define another term, that is called FH. So, FH is nothing but the schema fitness or average fitness of the string. Now, supposing that say 5 strings are going to follow a particular template, say schema H. Now, I can find out the fitness value of all the 5 strings which are going to follow a particular schema. We add their fitness values and divide by 5. So, that will be the average fitness of the strings which are going to follow the schema H, and that is nothing but the schema fitness denoted by FH. And this particular is the total fitness, summation F is nothing but the total fitness. Now, I can find out what will happen to the schema H at T plus 1th iteration if I know what is MHT. So, if I know that how many strings are going to follow a particular template at Tth iteration and what will happen to this particular schema H in the next iteration, that I can find out using this particular expression. So, MHT plus 1 is nothing but MHT multiplied by n multiplied by FH divided by summation F. Now, how to arrive at this particular expression? As I told that we are using the principle of proportionate selection. Now, proportionate selection is the probability is proportional to the fitness. Now, we have already calculated what is FH, that is the schema fitness, and I also know what is the total fitness, that is summation F. Then what is the probability according to the proportionate selection that this particular schema H will be selected in the mating pool? That probability is nothing but FH divided by the sum of all the fitness values. So, this is the probability that this particular schema H will be selected through this particular the proportionate selection. Now, if this is the probability value, now MHT plus 1 is nothing but MHT multiplied by n is the population size multiplied by this particular the probability. So, using this reproduction scheme, so I can find out this particular the expression. That means, what will happen to schema H at t plus 1th iteration if I consider only proportionate selection. Now, let us see what happens if I use the other parameters, other GA parameters. Now, this can be written as like your MHT plus 1 is MHT multiplied by FH divided by F bar, because this average fitness F bar is nothing but the sum of the fitness values divided by the population size. So, from this particular expression I can find out this expression. Now, I am just going to concentrate on the crossover, and for simplicity let me consider the single point crossover. Now, supposing that P c is the probability of crossover and capital L is the string length. Now, a schema will be destroyed if the crossover site falls within the defining length. Now, if we remember, the defining length is the difference between the last and the first, the fixed bit position. Now, if the crossover site falls within this defining length, there is a possibility that this particular template will be lost, and if it wants to survive, so we will have to take the precaution. Now, what is the probability that this particular schema whose defining length is nothing but your delta H, that is defining length, will be selected inside that particular the danger zone? That particular probability is nothing but delta H divided by L minus 1. Why is it so? Now, delta H is a defining length, and if the string length is L minus 1, so I have got L number L minus 1 places for the selection of crossover site. So, the probability that the crossover site will fall within the defining length is nothing but delta H divided by L minus 1. So, that particular expression I am just going to write here. So, the probability of destruction is nothing but delta H divided by L minus 1 multiplied by P c, because P c, that is the probability of crossover, is another probability, that is also a probability of destruction. Now, here there are two probability values, one is the P c, another is the delta H divided by L minus 1. Both are probability of destruction, but they are independent, and that is why we multiply these two probability values just to find out what should be the probability of destruction. Now, if this is the probability of destruction, so very easily you can find out the probability of survival, that is P s, is nothing but 1 minus P c delta H divided by L minus 1. So, probability of survival is nothing but 1 minus the probability of destruction. Now, if I just combine this thing along with whatever we got through the reproduction, that means, if we combine the effect of reproduction and crossover, so we will be getting the updating rule, that is M H t plus 1 is greater than or equals to MHT multiplied by FH divided by F bar, this part we have already seen, multiplied by the probability of survival, that is 1 minus PC multiplied by delta H divided by L minus 1. Now, this MHT plus 1 is greater than or equals to this particular expression if I combine reproduction and crossover. Now, let us see if I consider the mutation, and here I am just going to consider bitwise mutation. Now, if I consider the bitwise mutation, and we can say that to protect the schema, mutation should not occur at the fixed bits. Now, the number of fixed bits are denoted by the order of a particular schema. That means, on the fixed bits there should not be any mutation, just to preserve that particular the schema. Let P m be the probability of mutation, and this is nothing but the probability of destruction. Now, if this is the probability of destruction, then the probability of survival is nothing but 1 minus P m. Now, what is the probability of survival if I consider all the fixed bit position in a schema, that is denoted by P s. So, P s is nothing but 1 minus P m. So, 1 minus P m is actually the probability of survival for the first fixed bit, 1 minus P m is the probability of survival for the second fixed bit, and similarly we have got order of H, so many fixed bits. So, this becomes actually 1 minus P m raised to the power order of H. Now, as P m is very small compared to 1, so approximately we can write down it is equal to 1 minus order of H multiplied by P m, and this is nothing but the probability of survival. Now, if I combine the probability of if I combine the effect of reproduction, then single point crossover and bitwise mutation. So, I will be getting this is the rule for updating of this particular the schema. So, the rule for updating is MH t plus 1 is greater than or equals to MH t multiplied by FH divided by F bar multiplied by 1 minus PC delta H divided by L minus 1 minus order of H multiplied by P m. Now, this is nothing but the probability of survival if I consider this crossover as well as mutation. So, this is actually the probability of survival denoted by P s, and F h is the schema fitness, F bar is the average fitness, M h t is the number of GST going to follow schema H at tth generation, and M h t plus 1 is the number of GST which is going to follow the schema H at t plus 1th iteration. Now, here you can see that I put one sign greater than or equals to, not only equal, there is a reason behind that. There is a reason behind putting this particular the greater than sign. The reason is as follows. Now, during this GA operation, there is also a possibility that a new GA string may also participate or may also follow a particular schema, that is schema H. So, just to keep that particular possibility intact, so here I have put greater than or equals to sign. Now, let us see what does it mean, what is the conclusion from this particular the expression. Let me take a very hypothetical situation. Supposing that F h is greater than F bar, that is the schema fitness is more than the average fitness, say delta H, that is the defining length is short defining length, then comes OH, that is the order of schema H, that is say low. Let us see what happens. If I consider the schema fitness is more than the average fitness, then the defining length, that is this is short and order of H is low. So, what will happen? The probability of survival is going to be more, and moreover f h is found to be greater than f bar. So, there is a possibility we will be getting a higher value of this particular m h t plus 1 compared to your m h t. That means, at tth iteration, if I find out that only 5 bits are going to follow schema H, there is every possibility at t plus 1th iteration, there is a possibility that might be 8 strings are going to follow schema H, provided. So, f h is found to be greater than f bar, delta H is short and order is low. Now, in sentence we can say that if I can find out a schema whose average fitness is more than the average fitness of the population, and if it is having short defining length and low order. So, that particular schema is a very good schema, and that is going to receive more and more number of copies, and more number of GA strings are going to follow that particular schema. Now, in other words, we can say that the schema which is having this particular property is a very good schema, and which is going to make this particular search, which will be that particular very good schema will be the building block of this particular the GA search. This is almost similar to the situation. Supposing that we want to construct a very strong building, and to construct a strong building, the quality of the bricks is very important, and if you get very good quality bricks, so good quality bricks are nothing but the good quality templates or the schema, and if I can find out good quality schema, that will receive more and more attention, and its number is going to increase. And on the other hand, if I get a bad schema, there is a possibility the number of GA string going to follow schema H is going to be reduced with the number of iteration, and ultimately that particular bad schema may be deleted from this particular the population. Now, that means the fact which I am going to reveal, that if we get a very good schema, so you will be getting more and more copies. That means, as the GA iteration proceeds, there is a possibility that a majority portion of this particular population will be occupied by the very good schema, and there is a possibility that if GA is running properly, so you will be getting the multiple optimal solution. Now, there actually the fitness values will be the same, but that particular fitness value we can reach with different combination of the design variables. Now, this is another very big advantage of the GA, that we will be getting the multiple optimal solutions. Now, out of this multiple optimal solution, the user can select any one. Now, just to summarize, so I can say that, so this particular schema theorem is an indirect proof, mathematical proof for the convergence of this particular the binary coded GA. Thank you.